Welcome to this video. Today, we'll explore an important environmental challenge: how to turn food waste into green biosurfactants. Globally, the food waste issue has become a pressing concern. Every year, approximately 1.3 billion tons of food are wasted worldwide, accounting for nearly 1/3 of all food produced. This not only contributes to environmental problems such as greenhouse gas emissions, but also represents a significant waste of resources like water, energy, and labor. Addressing food waste is critical for global sustainability. In Hong Kong, approximately 3,400 tons of food waste are generated daily, making it the largest category of municipal solid waste. However, over 94% of this food waste ends up in landfills, with only 6% being recovered at OPARC. This not only places significant pressure on the environment, but also results in the loss of valuable resources. To address this issue, the Hong Kong government has taken various actions. Meanwhile, surfactants are an essential class of chemicals widely used in detergents, cosmetics, and food processing. The global surfactant market is massive, but traditional surfactant production relies heavily on petrochemicals, causing significant environmental harm. This raises an important question: can we produce surfactants in a more sustainable way? The answer is yes! By using food waste as a substrate, we can produce biosurfactants, turning waste into a valuable resource. So, what are biosurfactants? Biosurfactants are natural surface active molecules produced by microorganisms. Similar to surfactants, they have two distinct ends: a hydrophilic end that interacts with water and a hydrophobic end that interacts with oil. This unique structure allows biosurfactants to reduce surface tension and form micelles, effectively emulsifying oil in water. Due to their eco-friendly properties and versatility, biosurfactants are extensively utilized across various sectors, ranging from food and cosmetics to petroleum. Biosurfactants are already integrated into many everyday products. Examples include sophorolipids used in laundry liquids, dishwashing liquids, and shampoos. The biosurfactants market is experiencing significant growth, with an estimated compound annual growth rate of 5.17%. Among biosurfactants, sophorolipids, classified as glycolipids, stand out for their efficiency and eco-friendliness. Typically, the sophorose head is derived from glucose, and the fatty acid tail from oleic acid. However, these first-generation feedstocks have relatively high production costs with adverse environmental effects. Therefore, researchers have explored the use of second-generation feedstocks, specifically industrial residual biomass waste streams. Food waste and waste cooking oil, which contains sufficient glucose and free fatty acids, emerge as promising secondary feedstocks. Typically, the production of sophorolipids from waste streams involves several key steps. 1. Food waste, hydrolysis, and preparation as hydrophilic carbon sources. 2. Waste cooking oil preparation as hydrophobic carbon source. 3. Microorganism cultivation. 4. Inoculation and fermentation. 5. Separation and purification. It is the traditional two-step fermentation process, with a separated food waste hydrolysis and fermentation process. However, these multiple steps are time-consuming and costly, and the different temperature requirements increases investment and operational cost. To overcome these challenges, we propose simultaneous saccharification and fermentation process, where hydrolysis and fermentation occur in a single reactor, simplifying the process and reducing costs. However, in the SSF process, the complex raw substrates cause a sharp increase in viscosity within the bioreactor, which makes efficient mixing quite challenging. This means we need a better reactor design that can handle high viscosity systems and ensure effective mixing. We have developed and tested 4 types of impellers: the Rushton impeller, helical ribbon impeller, and screw mixing impeller. So, which impeller performs the best? For the screw-mixing impeller, the impeller width was insufficient to generate effective three-dimensional circulation within the reactor during hydrolysis, resulting in poor solid suspension, inadequate mixing, and low hydrolysis efficiency. Then let's have a look at the double Rushton impellers. It's obvious that the small blades cannot generate an efficient disturbance. However, although the large blade Rushton impeller can provide more efficient bulk mixing, the vertical mixing was insufficient to evenly mix the larger and heavier FW particles throughout the reactor. As for the helical ribbon impeller, the spiral structure can generate strong axial and radial flows, ensuring the thorough suspension and circulation of solid particles. CFD analysis confirms the helical ribbon impeller offers the best mixing performance due to its enhanced gas-liquid agitation and homogenization capabilities. As a result, the helical ribbon impeller achieved the highest hydrolysis efficiency and the highest final glucose concentration in the experiment, demonstrating its outstanding performance in high-viscosity fermentation processes. In addition, we also examined the impact of different helical ribbon impeller positions on mixing performance. In total, 3 positions were tested, and the lowest position demonstrated better mixing efficiency and lower energy consumption. In summary, by utilizing food waste and waste cooking oil as substrates, we've demonstrated a sustainable approach to produce biosurfactants through simultaneous saccharification and fermentation. Moreover, the benefits of this approach extend far beyond the environmental impact. It promotes social equity by creating employment opportunities and engaging stakeholders, while also driving economic growth through efficient supply chains and reduced production costs. Together, all of this works hand in hand with the idea of a circular economy, leading us toward a greener and more sustainable future. Thank you for watching. If you're interested in learning more about our research or collaborating with us, feel free to reach out. Let's work together to turn waste into value and create a better world.